Okay, Algebra 2 students, I appreciate you finding time to do your notes. Today we're going to continue on with our discussion of factoring, and we're going to be looking at three particular rules, and they are called the difference of two squares, the sum of two cubes, and the difference of two cubes. So if you would please copy down your title as well as your objective. And your objective for this day is the student will learn the special cases of factoring the squares and cubes. Now, these are going to be straightforward rules that we have to follow. We will have to get these rules memorized. These are typically not rules that are provided for us when we take tests like an ACT or an SAT or other similar college entrance type exams. So we're probably going to have to spend a little brain time getting these memorized. However, as you work with them a few times each, I think you will see that they're not all that difficult to get memorized. Just got to become familiar with them. Okay, so let's take a look. All right, one topic we're going to need to have a knowledge of before we can get to some of these rules is the idea of what is a conjugate. Okay, now if in a binomial both of the terms are identical except for their signs, they are called conjugates of each other. So there's a definition there. Okay, so put conjugate out on the left column and define it over in the center on the right side of the page. If in a binomial both of the terms are identical except for their sign, then they are conjugates of each other. And I have several examples here for you to look at to get the idea of what conjugates actually are. Okay, and there's a very simplistic one right there. Okay, we have two binomials. Okay, you can see that each of them has an x term, each of them has a y term, and the only difference is the sign between them. X plus y and x minus y are what we call conjugates. Similarly, 3x minus 4, 3x plus 4. Negative 2x minus 3y, negative 2x plus 3y. These are all examples of conjugates. Now, the thing that makes a conjugate actually a special type of situation is actually with conjugates, when they are multiplied times each other, we actually manage to eliminate part of the terms. As such, conjugates are actually used for a variety of things, particularly when we are trying to eliminate something from a problem. Like maybe we have a denominator in a fraction that we need to simplify somehow. Multiplying times the conjugate of that binomial might actually help you out. Okay, but anyway, when two binomial conjugates get multiplied, the middle term gets eliminated. Now, what we're saying here is if you have a binomial times a binomial, what we should expect is we should expect 4 terms out of this distribution. 2 terms on the left, 2 terms on the right, 2 times 2 is 4. Now, as we have seen with our binomials being multiplied, is a lot of times we catch a term or a like term, and we're able to combine it so it's not 4 terms, it actually simplifies down to a trinomial. Okay, but anyway, the straightforward math of this is, of course, every term on the left times every term on the right. So we've got x times x times negative y, and then we scooch over, we have y times x and y times negative y. Okay, we get 4 terms out of the expansion, like we just said, x squared minus xy plus xy minus y squared. Okay, now notice the 2 terms in the center there. They are like terms, same variables with the same exponents. They are both xy terms, so they can be combined. You have a negative 1, and then you have a positive 1. So when those are added together, you have 0 xy's, and you are left with simply the x squared minus the y squared. This is no accident. It is done on purpose. Okay, and we're going to use that fact for some of the rules that we're going to be using. Okay, so what we're saying is, therefore, if we were to take x squared minus y and factor it, we would be able to get the original problem back, which is x plus y times x minus y. Okay, now that is not an easy conclusion to arrive at. If you were given the binomial x squared minus y term, x squared minus y squared, and told to factor it, okay, this is not something that is common sense. We do not have a method to arrive at that. As such, we have a rule to accompany it. So let's take a look at the rule. This one is called a difference of two squares, and the reason is because difference, it is a subtraction problem, and two squares, we are looking at two terms that are both perfect squares, meaning something squared. So if both terms of a binomial are perfect squares and they are being subtracted from each other, then they are what we call a difference of two squares. And there is a straightforward rule that applies when you see this. Okay, a squared minus b squared. That is the generic form for a difference of two squares. Okay, and when you see this, you factor it by putting the a term plus the b term and then multiplying that times the a term minus the b term. You're just going to have to remember this, identify it when it happens in a problem, and force the values to follow this formula. Okay, so let's look at one in a problem. It'll help once we can get all the A's and B's out of there and start looking at some numbers. So here is one. Okay, we have a problem here, and the problem is to factor 4x squared minus 9. Okay, now we suspect that this might be a difference of two squares, but you absolutely need to check it to make sure. You definitely do not want to use the difference of two squares rule unless it actually is a difference of two squares. So the question is, can we take the 4x squared and make that some term times itself? Can we take the 9 and make that some term times itself? And the answer is yes, both of those can apply. Okay, so 4x squared, what times itself is 4x squared? Well, obviously 2 times 2 would get us the 4, and x times x would get us the x squared. Over there with the 9, what times what? Well, 3 times 3. So you can see in both cases we have the exact same term being multiplied times itself. So the rule says, since it is a difference of two squares, they're being subtracted up there, we're supposed to plug it into the formula, a plus b and a minus b. So where do you get the a and the b from? Well, they are the factors that you just discovered. One of them, a, is going to be one of these values, let's say 2x. The other one is going to be the other factor that you found, which is the 3. So when you plug in, this problem factors into 2x plus 3 times 2x minus 3. Again, that's not exactly common sense. You simply have to trust that that is the way that the rule works. Now, there's only really one hazard that we're looking at today, or we're going to mention. Okay, there is no such thing as a sum of two squares. We have a rule for difference of two squares, but actually the sum of two squares is prime. This guy will not factor. Okay, so do not try to apply the same rule as you just did with a difference of two squares. Sum of two squares will not factor. However, a sum of two cubes definitely will factor. Okay, so if you had something like this, and when we say cube, we are talking about some value times itself, and then times itself again. That would be cubed. Okay, so let's have a look here. The sum of two cubes. Okay, if both terms of a binomial are perfect cubes, again, meaning a number times the same number times the same number again, and they are being added to each other, then that fits the format for sum of two cubes. And when this happens, once again, there is a rule that applies, and it's a fairly complicated rule. Don't freak out at it. Okay, you'll get the hang of it as we work through some problems. But the rule says that you will multiply a binomial times a trinomial. The binomial will be the a plus the b. Okay, that's pretty much the same structure as your binomial was. Okay, a plus b. And then we're going to multiply that times a squared minus a times b plus b squared. Okay, that's going to take a little getting used to, but that is the rule. Okay, so let's take a look at this with something other than a's and b's. Okay, I didn't help you out much as far as numbers go because I gave you an example that has more variables in it. Okay, so let's take a look at this. Let's say we're supposed to factor x cubed plus p cubed. Okay, well, we see the cubes in there, the third power, so we would suspect something like a sum of uh, of two cubes. Okay, and so the question is, does the sum of two cubes apply? Can we take x cubed and break it down into some value times the same value times the same value again to equal x cubed? And can we do the same thing for p? Hopefully you can very easily see in this case that, yeah, that breaks down very easily. X cubed and p cubed factor down into x times x times x and p times p times p. Okay, so absolutely this is a sum of two cubes. Okay, so by the rule, we ought to be able to force this into this format, a plus b, and then multiply that times a squared minus a times b plus b squared. Okay, so when we plug everything in there, okay, it should look like that. Now be advised that sometimes there will be some simplification that may need to be done. For example, if x or p had been some kind of a number, then we might be squaring those numbers before we finish this problem. Or if p and x had both been numbers of some kind, then in that center term on the trinomial, we would have some multiplication to do. In this case, it turned out to be simplified right off the bat, so we don't have anything else to do. That is our answer. Okay. However, let's look at one that's a little bit more complicated so you can see what I'm talking about. Here we have 8x cubed plus 27. Okay. Seeing that x cubed in there ought to make us suspect that it might be the cubed rule, and we can see that there's a plus sign in there, so it might be a sum of two cubes. So once again, we're going to ask ourselves, does the sum of two cubed rules apply? Okay, well, let's check it out. Can we take 8x cubed and break it down into something times that same thing times that same thing to equal 8x cubed? Well, 2 times 2 times 2, that's 8. And of course, x times x times x, that's x cubed. So that looks good. How about the 27? Well, 3 times 3 times 3 is actually 27. So yes, we can actually break this thing down, and we can see that 8x cubed and 27 are both perfect cubes. Okay, so going into the formula, a plus b times a squared minus a times b plus b squared. Okay, using 2x and 3 as our a and b, it temporarily looks like this mess. Okay, now on the left side over there, there's nothing to combine. 2x and plus 3, those are not like terms. They will not add. However, 2x needs to be squared. Can that be simplified? Can we take 2 and square it? Of course we can. That would be 4, and of course the x squared is x squared. In the middle term of the binomial, you've got a negative 2 times a 3. We can simplify that into negative 6, and of course the x will still be there as well. And the trail term in the trinomial there, 3 squared, of course is 9. Okay, so you can see when numbers are involved, there is a little bit of simplification that needs to happen before those problems are done. Okay, there is one more rule in today's stuff, and it is the difference of two cubes. Okay, now I bet you can guess the way this thing is worded, same as the other ones. If both terms of a binomial are perfect cubes and they are being subtracted from each other, then that is the textbook definition for difference of two cubes. And once again, you're going to see we have a formula. And once again, you're going to see that the formula is rather ugly. Okay, but again, don't freak out too bad, because if you're paying attention, you will see that this formula is not hardly any different from the sum of two cubes. There's only two little changes on this formula from the last one. First off, the last one was a sum of two cubes. This one is a difference. Take a look at the binomial, a minus b. For the sum of two cubes, that binomial is a plus b. So when the problem was a plus, the binomial was a plus. And now we're looking at the binomial being a subtraction problem. So our factorization starts off with subtraction as well. There's one other sign change that you might be noticing, and that is the sign of the second term in the trinomial. For the sum of two cubes, it was minus ab. For this one, it is plus ab. Okay, so basically what you can kind of remember is that the b squared term back there for both of these cubed formulas is always plus. Okay, but the change between the sum of two cubes and the difference of two cubes is it flip-flops all of the other signs. Okay, so maybe that'll help you remember it a little bit. Anyway, let's see if we can see this formula in action. Okay, here's a problem. Okay, we have 125 m cubed, and from that we're going to subtract a z to the sixth. Okay, well, we should suspect that possibly one of the cube formulas is in play here, because first off, we do have a variable that's to the third power. And we have another variable that's not to the third power, he's to the sixth power. However, that is a multiple of the third power. 6 is a multiple of 3. Okay, so it might very well be a difference of cubes. Okay, so let's look at it. Does difference of 2 cubes apply? It actually will. Okay, so let's take a look at 125 m cubed and z to the sixth. See if we can't break them down. 125 m cubed. What times what times what gets you 125 m cubed? Well, 125, that's 5 times 5 times 5, so that one's easy enough there. And m cubed is m times m times m. Okay, so 125 m cubed is a perfect cube. How about z to the sixth? Now, obviously, we can't go z times z times z like we have been doing and get z to the sixth, but can we change the exponent of the z and get to z to the sixth? Absolutely. If we went z squared, z squared, z squared, those twos add up by the laws of exponents, and you have z to the sixth. Okay, so by the rule, okay, we ought to be able to force these terms into the formula a minus b times a squared plus ab plus b squared. Now, obviously, our terms are for the a and b are 5m and z squared. Okay, it's going to look awfully ugly here for a moment, but we'll clean it up. Okay, again, on the binomial, there's nothing to do. Okay, but there's plenty of stuff we can do to clean up the trinomial. Okay, the lead term on the trinomial, 5m, wants to be squared. 5 squared is 25, and m squared is m squared. Okay, in the center term on the trinomial, okay, there's nothing that can combine there. You've got a 5 and you've got some m's and you've got some z squared, so they're just going to all kind of coexist in the center term. But on the trail term in the trinomial, you have z squared squared. Okay, remember back to your laws of exponents. What is the math that happens when an exponent is raised to another exponent? That is when you get to multiply. So where z squared squared means z to the 2 times 2, which is 4, be z to the fourth on that trail term. Okay, so that's how it simplifies. Now I have 3 examples that I want you to copy down. Okay, they obviously are going to go along with the 3 rules that we just discussed. I want you to look at the examples, try to figure out which rule applies, and then apply it to get the correct factorization. First example is 81m squared minus 25. 81m squared minus 25. Copy it down, figure out if there is a rule that applies, apply it if there is, and get the factorization. Second example, b cubed minus 27a cubed. b cubed minus 27a cubed. Copy it down, look at your rules, decide if there's a rule that applies. If there is, apply it and get the factorization. And the final example, x cubed y cubed plus 64. X cubed y cubed plus 64. Copy it down, look at your rules, figure out if there's a rule that applies. If there is, apply it and get the factorization. If you would please get those 3 done, bring them with you to class. I appreciate you finding time to get your notes taken care of, and we will see you in class.